Hello, Dr. Botan and Gabriel Campos. My name is Zachary Cohen, and I'll be presenting on the Robinson R44 landing skid redesign. If you refer to slide 8 of the presentation, you'll see my portion of the project. Moving on to slide 9, the figure on the left shows a solid body where the sum of the forces and the sum of the moments is equal to 0. The figure on the right shows a two-dimensional Mohr circle and the equations used in constructing it. The next slide shows the maximum landing characteristics for an engine failure between 8 and 500 feet. This information was derived from the Robinson R44 user manual. Using these maximum landing characteristics, the maximum landing loads were then derived. The next slide shows these maximum landing loads. A sample calculation of the vertical maximum landing load in the y direction is shown. This calculation accounts for both the weight of the aircraft and the impulsive force of the aircraft upon landing. The next slide shows these same forces applied to the rear vertical strut, and then the figure on the right shows a realignment of these forces along the axis of the part. The reason for doing this was to make the internal reaction moments easier to calculate. The next slide shows the shear diagrams created with these external loads, and then using these external loads on the next slide, the moment diagrams were created. From these moment diagrams, the maximum moments, as well as the location of the maximum moments, were determined. Then using the compressive stress equation on the next slide, and iterating it over the outside of the hollow tube, the location of maximum compressive stress was determined. Once the maximum compressive stress was determined, the outer radius required to ensure a safety factor of 1.5 was determined, as can be seen in the equation at the bottom of the slide. Of course, the internal shear forces were also calculated, and these forces can be seen depicted in the figure on the right in the next slide. Using these compressive normal stresses as well as the shear stresses, a stress element for the point of maximum compressive stress was determined. Then the figure on the right shows a Mohr circle for this particular stress element. The next part of interest in this design was the horizontal I-beam that connected the left and right half of the landing skid. As can be seen on the right, all of the loads applied to the free end of the horizontal I-beam are very similar to the loads applied to the bottom of the rear strut. However, the free end also has reaction moments applied to it, and this is because the forces that acted at the bottom of the rear vertical strut acted at a distance away from the free end of the I-beam and thus induced reaction moments. So using these external loads, the internal shear diagrams were constructed. Then using these shear diagrams, the moment diagrams were constructed. Then similarly to the last case, using these maximum moments and their locations, the location of maximum compressive stress was determined. Using this location of maximum compressive stress and the associated shear, the stress element of this point was constructed and can be seen on the next slide. The Mohr circle for the stress element is shown on the right. The last component that had to be considered in this design was the bottom horizontal strut. As can be seen in the figure, this part is statically determinate. The reason this part is statically determinate is because all of the external loads were balanced by the reaction loads of the rear vertical strut. Thus, the only real force that had to be considered was the compressive stress on the cross section shown to the right. On the next slide, we can see the calculation for this compressive stress. We see that the magnitude of these compressive stresses is much lower than the rear vertical strut and the horizontal I-beam, and so we don't expect this part to fail. So last two things I want to talk about are buckling and von Mises stress. So as can be seen on the next slide, the critical buckling stresses were calculated for the rear vertical strut and the horizontal I-beam. For the horizontal I-beam and the rear vertical strut, the safety factor was calculated to be 1.33 and 1.101 respectively. The next slide shows a von Mises stress calculation. So using the von Mises stress, the safety factor for the horizontal I-beam and the rear vertical strut were determined to be 1.53 and 1.61 respectively. That concludes my presentation. Thank you very much and have a nice day.